Hi, I'm Clinton. It's very nice to meet everyone virtually from this record video presentation. This presentation is basically for my final project in optical communication course. We will discuss about neuromorphic photonic networks, which is a silicon photonic system that can perform neural network computing with high speed, high bandwidth, and low power consumption. And also, we will discuss its application for optical communication. So this is the table of the content for today's presentation. First of all, I will try to explain what did I have learned about silicon photonics. Imagine a tiny speaker as big as a microchip, smaller than a coin, and made entirely out of silicon. Yes, that speaker, that's the miracles technologies, what we call as MEMS. MEMS are microsystems with both electric and mechanical functions, built with the same advanced techniques that make today IC. MEMS are everywhere around us. If MEMS is the result of applying modern nanoscale CMOS processes to the mechanical world, then doing the same for the optical domain gives us silicon photonics. Okay, now we know that there are two words in this part, silicon and photonics. So let's start from photonics and what does it mean. Photonics technology transmit and manipulate light in the form of light particles or photons. It is related to the word of optical data transmission. Previously, networking companies communicated using electrical signals sent through copper wire. The issue is that the electron traveling through such wire interact with the other atoms, which slows them down and generates heat. By the 1990s, networking companies found themselves struggling to deal with exploding data traffic by the network demands. They revolutionized long-distance communications by switching the using light, sent via optical fiber, to efficiently transmit data across great distances. Light moves through optical fiber at the speed of light, so nothing is faster than the speed of light. And this lets us transmit optical signals at super high frequencies, which means higher data volume transmissions. Later on, engineers took the concept yet another step forward that can sending multiple different light wavelengths that won't interfere each other with other signals in the same fiber by using different light wavelengths. For today, optical fiber technologies dominate the long-distance communication space. Over around 2 billion kilometers of optical fiber have been deployed. Now we move to talk about silicon. The nanoelectronic industry has been using silicon for decades. The element is the single most widely studied element in human history. It is low cost and allows for massive scale. It is plentiful. People have been able to make silicon to do amazing things. Billions of transistors on one wafer and entire system on chip that are faster, smaller, and cheaper than their priors. And for that reason, engineers have wanted to bring the big scale of modern CMOS manufacturing over to the photonic world. Furthermore, transistors and traditional chips right now are still communicating using electron through wire. The idea is what if we were to replace those wires and electrons with combination of optical fibers and light? The idea of monolithic silicon photonics chips is to make everything on it being made on single material system which has capabilities to transmit and manipulate light. From 1970, the system would have five components. One, a light source, usually a laser. Two, routes and pathways to manipulate light, to bend it, guide it, filter it, couple it, split it, and combine it. kind of like optical fiber does, but just within the integrated chip. These are broadly referred to as a passive structures, but with different shapes and structures with their own names. The next are the ways to convert digital electronic signals into digital optical signals and vice versa. The former is called a modulator. The latter is photodetector. A component that can do both modulator and photodetector work is called a transceiver. Next, we need traditional CMOS electronics to accompany the various photonics components that we have mentioned before. These serve support functions like encoding and decoding certain data items. So there we have it, a complete photonic systems that researchers are trying to incorporate all into a single monolithic chip. Now let's move to other related topic for this presentation. We know that AI is all around us and there are numerous applications such as NLP in Siri or Google, then game playing AlphaGo, recommendation systems such as YouTube, Netflix, Amazon, self-driving car, even in healthcare. These AI systems are enabled by neural network. The problems on today's modern era is the usage of computational power to train neural network was doubling every 3.4 months. According to the Moore's law, our computer capabilities also was doubling every 2 years. The current situation cannot just satisfy this computer power that's required for this type of AI-based system. So there has been a need to go from software-based neural network on standard digital computers to more specialized computers, which we call neuromorphic hardware. This table are the differences between electronics and photonics when looking into any computing, communications, linear algebra, and system paradigm. Some of these things are easier in electronics, and some other paradigms are easier in photonics. The reason why we wanted to use photonics for neural network computing is photonic is perfect for interconnect. It has extremely low loss, which means it consumes almost no power when moving the data across the photonics processor. And the photonics also have very large bandwidth in contrast to electronics. For these reasons, photonics neural network can achieve efficient and ultra-fast neural network computing that are exactly led by optical communication system. On the next slide, I will provide a brief overview of photonics neural networks. Then, we will discuss a specific implementation with silicon photonics, which is proposed by CERN 2021 on optical communication. And we will discuss why photon neural networks are especially suitable for this application. The basic operation on neural network, we have linear part of the neuron where we are doing a dot product of two vectors. And then after that, we have a nonlinear operation where we are doing decision making. The way we do this with optics is that we use wavelength multiplex approach. We have multiple frequency of light which can encode information. So we can have a vector x that that can be put on multiple frequencies or colors of light represented here. And then the signals get weighted by array of microresonators. The microresonator can work as wavelength selective filters, and it can be tuned by change the transmission of the signals at different wavelengths. We can see this approach can perform a function, which is the most dominating function in the neural network, using only passive devices in a parallel way and at speed of light, which shows a big contrast to electronic devices. And after being weighted, the signal is detected by a photodetector, and it will receive the total optical power and converting to photocurrent. So the summing function is provided by the photodetector. Then the photocurrent is amplified and drives the optical modulator after it. The transfer function of a modulator is usually nonlinear, so we can use this to perform the linear function in the neural network. The optical components involved in this system including the microarray, the photodetector, and the modulator can all be fabricated with the standard silicon photonics facilities. And the performance, including the speed, the bandwidth, and the power efficiency of all these devices, have been jointly optimized by the whole of optical communication industry. We have number of applications before, and we will talk one of them because of the time. So this is in fiber optic communications, and I will try to explain my best to explain this. So in this system, we have very long pieces of fiber, and when we have long pieces of fiber, we have a lot of nonlinearities like chromatic dispersion and so on. What happen right now is typically DSP techniques, where we are when we are then compensating for this nonlinearities, for example, in this commercial chip system. The challenge is we need able to go from the analog domain into the digital domain, and we are placing a lot of constraints on the analog to digital convergence. On the conference talk by Bavin, they implemented very simple 2 by 8 by 2 feed-forward neural networks that solving a regression problem. And they showed that we can compensate for those nonlinearities and do it equal to, or if not better than, what can be done this digital backpropagation. Now, if the signal is already in the analog domain and is already in the optical domain, the preposition is, can we use these very fast neural networks in this network and process them in real time? And this can be alleviate some of the challenge on the DSP. What we are able to is implement this type of neural networks and then post process. So we are able to train these neural networks using regression problem and then estimate the amount of nonlinearities that we have, and then subtract that nonlinearity from the received symbols, and then compare the received symbols with the symbols that we were sent, and then measure the bit error rate. So we are able to train, and um, so we were able to implement one of this hidden layer here of this neural network using neuromorphic photonic chips. Implement one of these hidden layers. And this is the way we ended up training the chip. So we train it offline using standard computers to solving regression problems. And we were using the neuron on chip and the nonlinearities, for example, in this case, to Lorentzian line shift function. And we send this data to the chip. We apply the nonlinearity and then use this in a loop. And then keep training until we can maximize the quality factor. Ons have done estimate amount of weight and bias for the modulators and photodetectors, and we convert this into equivalent voltage and current, and then upload them into silicon photonic chip. Experimentally, they were able to improve the quality factor by around 0.6 dB using these neural networks. And if we use software-based neural network, we can get around 0.65, and it's degraded by 0.05 compared to numerical simulations on software based. So this is a conclusion of my final project. The silicon photonics can enable large scale neuromorphic processes. And we need to look applications for the notes from this presentation, from this project. We need to look applications where it makes sense to use optics rather than just using them for applications that electronics is already very good at. Is if electronics is already good at, we don't need to use the optics instead of just using it. Okay, that's for my presentation today. Thank you for listening.